Radio Society. We are honored to have Shanaka Jayasurya, and who is a program coordinator at the United Nations Office of Drugs and Crime, UNODC. If I got it correct, Shanaka, correct me if I'm wrong. And I think Shanaka is currently stationed at Thailand, and he has been a long-term member of the RSSL as well. And with his extensive knowledge and experience in the maritime industry, and also maritime communications and safety and anti-narcotics, he will go on to introduce himself, I believe. So I believe Shanaka will bring in valuable insight today to our session, and also touch the multiple uses of AIS technology, which is our theme today. And of course, Shanaka is joined by Mr. Robert Tremlett. Robert is an internationally acclaimed, a renowned expert in maritime communications, surveillance, and navigation. And he's also an expert in satellite communication, particularly AIS technology. So we are extremely honored to have both of you, Shanaka and Robert. And without further ado, and passing more time, I will pass it over to you, Shanaka, to continue this session. And thanks again uh, for accepting our invitation and conducting this session. Over to you, Shanaka.
Thank you very much, Taranga, and good evening to everybody. And a special thank you to Ron for putting this all together with Taranga. And this evening, I was looking at a T-shirt I had of the Radio Society of Sri Lanka, but I tried to wear it for the presentation, but I couldn't even get my arm into it, which shows that I have put on too much weight. But I have been with the RSSL for some time now. And currently, as Taranga mentioned, I'm the program coordinator for Southeast Asia and the Pacific of the Global Maritime Crime Program of the United Nations Office on Drugs and Crime, and I'm stationed in Bangkok at the moment. So what I'll do is, it's a tag team event today with the expert Robert Tremlett working on the more interesting technology part of it. I will try and cover how we use AIS technology for maritime law enforcement purposes. Can everybody see my screen?
Yes, Shanaka, you can see.
Yes, Janaka, yes.
Okay, so what I'll try and do is to give some context as to why we use AIS, or Automatic Information System, that vessels use to provide their location for law enforcement purposes. And there are multiple users of use of AIS, but for us, the important thing is to locate what are known as vessels undertaking illicit activity, which we refer to as dark vessels. I just thought this was a very interesting cartoon, because very often we try to reinvent the wheel. And here is a case where we are using an existing technology which is meant for accident or collision avoidance for a law enforcement purpose. So what I will try and cover in my quick 10 minutes of the presentation, and then I'll pass it on to Robert to actually dive into the technology part of it and the more interesting technical aspects of AIS technology. I will give a background to maritime drug trafficking, which is the area of work that I focus on. Then I will refer to cooperative technologies and non-cooperative technologies. I will kind of demonstrate how the overlay of cooperative and non-cooperative technologies are used. And then I will kind of go into AI and look at how predictive behavior is being identified using new technologies in maritime domain awareness, or what is known as MDA. So for us at the Global Maritime Crime Program, we focus on multiple types of criminal activity that is taking place at sea. And we support the 193 UN member states many of which are littoral states or coastal states, to counter these criminal activities out at sea. And our role is to build capacity, enhance their technological capabilities, and provide support to undertaking operations. If we look at the Indian Ocean and what is known as the southern route, heroin produced in Afghanistan comes out from the Makran coast, which is the coast between Pakistan and Iran, near the Balochistan coast. And it moves into the Eastern African coastline with smaller routes that are moving to Maldives and Sri Lanka, and also to Yemen. But this is mainly known as the southern route of Afghan heroin coming out of the Makran coast. If you look at the Andaman Sea, you'll see that methamphetamine produced in Myanmar is trafficked along the coastline of Thailand and Malaysia and down to Australia as well. And these are all maritime routes that are being used by drug traffickers along the Andaman Sea. If you look at the Pacific Ocean, and I have focused on Southeast Asia and the Pacific because this is the region that I cover, and the region that I cover is Southeast Asia and the Pacific. We have cocaine coming from Latin America, and there are drop-offs done in French Polynesia or Tuvalu or Tonga, Cook Islands, and then move to New Caledonia or to Papua New Guinea, and then down to Australia. So there are multiple layers or transfers that take place, and these are usually trafficked using yachts or small craft and move across the oceans. So the picture I want to create is that while there is a significant amount of legal traffic that is taking place in the maritime space, there's also illicit activity or illegal activity. And how can we use technology to identify these illegal behavior of vessels that are plying the oceans? So these are the Arabian dhows that are used to move the heroin from the Makran coast through to the East African coast and also to Sri Lanka. And here I have got some photographs of some drug seizures done by the Sri Lanka Navy. And you'll see in the background those types of dhows that have been used to traffic drugs down to the equator or in the region of the southern coast of Sri Lanka, where it's picked up by Sri Lankan fishing vessels. So where do we come in? Where does the Global Maritime Crime Program of UNODC come in? And how do we support member states in enforcing drug enforcement capabilities out at sea? We use a lot of satellite technology, and I've just put in this thing about polar orbiting satellites, and I'm sure Robert will go into more detail. There are satellites that orbit the Earth on a regular basis, and most of them travel over the northern parts of Norway, and most of the receiving stations are up in the northern parts of Norway, because at every polar orbit, it comes over the North Pole. And as a result, it's easier to download all the imagery and that has been taken during their orbit when it overpasses the northern tip of Norway. So we use multiple sensors, and these are acquired using satellite technology and also terrestrial-based technology. The first type of sensor that we use is known as automatic identification system. And many of you who have been on a ship or have been on a vessel, you would be aware that vessels over a certain weight, I believe 300 gross ton, is mandated to carry a AIS on board. But even smaller vessels do carry AIS. This is a collision avoidance system. It's not a law enforcement system. It's to ensure that vessels do not collide with each other, and the vessels that are plying the oceans know where other vessels are. And Robert will go into more details on how AIS actually works. I'm more on the law enforcement side of things and focusing on the operations, but Robert is the expert on the technology part of things. There's also long-range identification and tracking, LRIT, another type of transponder where the signal is sent to the flag state. So every vessel that is out at sea has to be registered to a state, to a flag registry. And the LRIT provides information to that state of where the vessel is. But this information is not available to the general public. It's only available to the respective flag state. The other type of sensor that is available is what is known as VMS, Vessel Monitoring System. And this is used primarily by fishing fleets, by fishing vessels. So we have in Sri Lanka what are known as multi-day fishing craft and trawlers that go out to sea. They all have to carry a VMS system on board. So the VMS signals are collected by the respective countries. So the VMS is not available to other countries. It's only available to the country to which the fishing vessel is registered, and they are able to collect that information. And the VMS also includes additional information such as the size of catch and other related information relating to fishing. So this is another sensor that is being used. Very common, most of you know, terrestrial radar. So coastal maritime radar that you have on the coastline. And optical imagery, electro-optical imagery is another source of data. Now, if we take electro-optical imagery, on the second photograph on this presentation, you'll see that there is a significant amount of cloud cover. So it's very difficult to determine when electro-optical image can be taken where cloud cover doesn't obstruct. So to overcome obstruction of cloud cover, there is something called synthetic aperture radar that is used. So these are radar imagery of vessels out at sea taken by a satellite. We don't get the level of clarity in terms of what the vessel looks like, but we know that there is a vessel and the heading in which direction it is going, and the confidence in depending on the length. It can tell you the length of the vessel within a certain confidence ratio. And the last but not least is the most modern type, the most advanced technology, and this is just emerging. This is called RF detection. And at the moment, it's being undertaken by a company by the name of Hawkeye 360. If you Google Hawkeye 360, they're the ones who are able to provide RF detection imagery in the ocean space. So they have constellations of 3 satellites times 6, which are orbiting the Earth all the time. And because they orbit as a constellation of 3 satellites, they're able to triangulate any RF signal, including the signals from the VHF band, UHF band, right through to, I believe, the X-band radar signals and beyond. So, and also to the Thuraya band as well, the satellite phone band as well. So this is the most modern and most advanced version, but the imagery is very expensive. But what do we do with all this imagery that we can take? We have, as I mentioned, AIS, LRIT, VMS, we have the coastal radar, we have synthetic aperture radar, we have RF detection. What do we do with it? We do something called overlay. So we lay each of these imagery for a polygon or an area of interest over each other, because what the vessels that have switched their transponders on, they will be picked up by the AIS picture. Vessels that have the LRIT on, that will be picked up by the LRIT picture. Vessels which has the VMS switched on will be picked up by the VMS picture. And if there is a coastal radar, that will pick up all the vessels in the nearby, in the region that the coastal radar covers. Optical imagery will cover if there is limited cloud cover, and synthetic aperture radar will do the same. But what we are looking for here is the dark vessels. Now, this is a picture where if you look at the white circles, they have their AIS switched on when a synthetic aperture radar image was taken. So we have correlated the white circles with the AIS overlay. We have correlated the yellow circles with the VMS overlay. So these vessels are having their transponder switched on. But what you see in this synthetic aperture radar image taken from a satellite is there is a vessel that we have colored in red. Now, this is what is interesting for us. There is a vessel that is not having a transponder switched on, but it's out there in the sea. And this is an anomaly, or this is something suspicious for us. And these are the vessels that we are looking for using this technology to look for those dark targets. Why is this vessel out in the ocean without having any transponder switched on? Is it that the transponder has broken? Is there some mechanical defect? Or is it intentional? If it's intentional, are they engaged in legal or illegal activity out at sea? So this is the kind of activity, this is the kind of use of the multiple sensors using AIS and other types of technology that the Global Maritime Crime Program uses it for maritime law enforcement purposes to help member states to locate vessels that are out at sea but are keeping their transponders switched off for any particular reason. We also use what is known as human intelligence. It's very important to work with coastal communities because as much as you use technical intelligence or SIGINT, the human part is as important as the SIGINT part. So we train Coast Guards and other law enforcement agencies to build rapport, build connections with coastal communities, because when a fisherman goes out to sea and he sees an anomaly out at sea, a vessel that he has not seen before, if he can report that to the surveillance center when he gets back, you can use the technical sources to verify or corroborate that information and identify what that unusual phenomenon was, or why that vessel was in that region, which had never been seen before. Now what's happening is this type of technology is being used with artificial intelligence to do predictive behavior. So I mentioned to you that when the AIS signal is switched off, we don't see the AIS on the screen anymore. But what technology can do is it can predict using previous behavioral patterns. It can predict where that vessel could be. So these are some predictive approaches. So it looks for drift. It looks for encounters at sea. It looks for port calls or anchorages. It looks for sudden changes in headings that it has done in previous track data. So companies have bought all the track data of all the vessels in the world for the last 5 years. And if a vessel switches off its AIS, either intentionally or unintentionally, the algorithms will start to give predictive behavioral patterns, saying, okay, this vessel has gone dark, but in our view, 5 years ago or 3 years ago, it did the same thing in another region, and this is what it did. It moved in this direction, or it moved in that direction. So we would be predicting that it could be the highest confidence ratio of predicting is it could be in this region, or the second confidence is in this region. So it could provide you with predictive behavioral patterns. So that's where the maritime domain awareness technology is moving, where it's using historical track data to do predictive work of vessels that switch off their AIS, which is very helpful for law enforcement personnel, because as soon as a AIS is switched off, you can then start to use AI to try and predict what it's attempting to do. And finally, this is AIS spoofing. Now there is equipment that is also available in the commercial market, where you can give false locations for your AIS information. So that's called AIS spoofing. So this was a vessel that was coming. We were monitoring it because it was approaching the Bay of Bengal and on the eastern coast of Sri Lanka. And suddenly, we noticed that it had gone close to the South Pole. So they had used some kind of commercial technology that is available to spoof their AIS location. So this is the kind of the users of AIS. I will now pass the floor to Robert, who is the expert in the technological field, to provide you with some more details relating to the technology side of AIS. Robert, can I pass the floor to you? Before that, can I ask if there's any questions on the law enforcement part of the use of AIS? Okay, no questions. Robert, over to you, Robert.
Okay, firstly, I'm trying to, are you able to see the presentation?
Yes, Robert, we can see.
Good, good.
If you want to make it full screen.
Yeah. Okay, I can't see you guys anymore, but I don't think that matters. Okay, a very, very interesting topics described by Shanika very eloquently. I just want to talk a little bit about the technology, the limitations side of it. The first thing that we need to consider is what spectrum is used for the different technologies. You heard Shanika talk about AIS. Well, in fact, there are 2 AIS channels, and those are used by all AIS transponders. AIS itself was designed, as Shanika said, for collision avoidance and also for VTS. But it has been used for many other applications since it was first invented. Very quickly, the satellite community decided that they would like to be able to receive AIS, the terrestrial AIS being broadcast on AIS-1 and AIS-2. Indeed, because of this, the IMO and IALA went back to the drawing board because they found out very quickly that to receive the terrestrial AIS from satellite was problematic, because the AIS terrestrially is designed to only be broadcast for some 20 nautical miles, line of sight of the VHF. And so therefore, the satellite would have a view of many hundreds of these AIS cells, and I'll show you an AIS cell a little bit later. And so long-range AIS was invented, and this uses 2 more VHF channels, as we see there, 156775, 156825. These channels can only be used for the transfer of a small, very comprehensive AIS message, whereas AIS 1 and 2 will send all sorts of information, routing information, the speed, the draft of the ship, obviously the ID of the ship, etc. The AIS long range only sends a very brief information set, the latitude and longitude, the ID, and also the course made good. It does not show the ship's heading. AIS 1 and 2 terrestrially show the ship's heading. And so satellites still would like to have the AIS 1 and 2 because the ship's heading compared to the course made good will show if a vessel has another vessel alongside, if the vessel is in trouble, etc., etc. Other than AIS, we also have application-specific messages. And those are designed, for example, for navigational aids. We also have a new navigational aid, which is emerging in the market, which is called an ARMD. The ARMD is to try to stop the plethora of illegal fishing AIS floats which are being used around the world. The AMRD will only be used for Class A vessels and also for navigational aids. There is a new toy on the block, which is called VDE, VHF Data Exchange. AIS now moves away from its own domain into VDE. In fact, AIS is now part of VHF Data Exchange. And VHF Data Exchange will enable the transfer of information machine to machine, shore to ship, ship to shore, ship satellite, shore, shore satellite ship, or ship satellite ship. VHF Data Exchange already has some polar orbiting satellites, and the specification of the coastal stations is already set. There are still negotiations going on at IMO, or discussions, shall I say, in the NCSR committee for finalizing the specification of a shipboard VDE receiver or transceiver. But it's important to realize that there are a number of frequencies in the VHF spectrum which are now assigned only for these use. As I mentioned briefly, we have terrestrial AIS messages and we also have satellite. Let's have a look at the terrestrial messages. There are several different messages for terrestrial use. Messages 1, 2, and 3 contain the dynamic information for Class A. And these are nominally transmitted once every 6 seconds. For a very fast vessel, the transmission rate will come down to 2 seconds, and for a very slow vessel, the transmission rate will slow down. Message 17 is used for sharing DGPS or DGNSS, differential global navigation satellite system corrections. So we have DGPS stations around the world which monitor the received information from the satellite. They know where the station is, and therefore they can find the errors and then transmit those errors to ships which have suitably equipped receivers. Message 18 gives us the dynamic information of Class B, SO. SO is important. Class B SO came into being in 2017, and this particular AIS enables the Class B to fit into a time slot sharing with Class A. Class A still has priority, but Class B can also be assigned a slot. There is also a Class B CS, and most small vessels in the world will be using Class B CS, not Class B SO, because Class B CS has been around for more than 20 years, but it is not allocated a slot. And therefore, if the VDL loading of AIS is very high, it is unlikely or problematic that Class B carrier sensitive will actually be received. Then we have message 21, application-specific messages. I mentioned them earlier. And message 5. Message 5 gives the static information of class A, and that includes the voyage information, the draft, etc., etc. And message 24 for class B. The message 5 is quite a cumbersome message, so it uses 2 slots. And it's transmitted once every 6 minutes. It is very useful for MDA because we're able to know the characteristics of not just the speed and velocity, but also where the ship has come from, where it's going to, what its route is going to be, etc., etc. However, message 5 and message 24 are put in manually, and therefore it's very easy to spoof. Terrestrial AIS is designed for continuous situational awareness for VTS and collision avoidance, but it is only designed and regulated to be carried by Class A vessels. As Shanika said, that's vessels over 300 gross tons, or indeed over 500 gross tons if they stay in a coastal area. Class A also has to be used by all passenger vessels, irrespective of size. The satellite segment can receive satellite terrestrial messages and can sense the terrestrial messages 1, 2, 3, 5, 18, and 24. However, we get a lot of message collision because 2 vessels, which might be 300 nautical miles apart, might be transmitting on a slot assigned to it by vessels in the location of that vessel. And so we get a lot of message collision, and this, if we get a collision between more than one vessel, then we are likely to not receive any information at all from those vessels until one of them moves into another cell and therefore is allocated a different time slot. The other problem with SAT-T is that it can very quickly saturate the availability of receiving AIS by satellite. There is something now also called dynamic AIS. And Spire in Luxembourg now, who have joined, in fact, with the Exact Earth, now provide dynamic AIS. Dynamic AIS is where the ship's receiver, the ship's AIS receiver, retransmits the AIS data, the track data, from the ship via satellite to Spire, and Spire will then circulate that through various platforms. This is much better data than we will get by just trying to receive AIS, terrestrial AIS, by satellite. In fact, the quality of dynamic AIS is as good as coastal AIS, but it can only be used from suitably fitted ships. And therefore, if we look at dynamic AIS, we will see corridors of where ships ply regularly, large ships, probably container ships, gas carriers, etc., passenger ships. They will carry dynamic AIS, but other areas of the ocean which are not frequented by those vessels will not be able to provide dynamic AIS. So here we see a cell, an AIS cell. Hopefully you can see that there is an antenna down the bottom of the graphic. that would be where an AIS base station was. And the AIS base station is able to control the transmission rates, the timing of every vessel within its cell. Even if the ships are away from the coast, they still form a cell. And the AIS is quite clever because it will find a slot where nobody is transmitting, and then the ship will start transmitting on that slot. And when a new ship comes into a cell, it then hunts for an empty slot, and the AIS, Class A AIS receiver will then start broadcasting on that empty slot. And there are many hundreds, if not thousands, possible AIS slots. So Class A and Class B SO, I'm sorry, I cannot remember what SO stands for at the moment, but believe me, it's called Class B SO, self-organizing, that's it, will be allocated a time slot. Whereas Class B CS, carrier sensitive, is received by base stations and vessels, but cannot be received by satellite. It's only a 2-watt transmission, and therefore it's unlikely that a satellite will receive it. And it's going to struggle to find a slot anyhow to transmit, especially in busy waters. Base stations are very important. Base stations of a coastal state can manage an AIS cell. They can actually take certain classes of vessels which are in AIS range, such as those which might be piloting into a harbor or into a river. They can put those on a different channel and then monitor them on that new channel. So they can regulate what channel the AIS will transmit on, when the AIS of those vessels will transmit. They can increase the rate or decrease the rate of transmission by any classes of vessels or any particular vessel, so that they can manage all the vessels which are in the AIS cell. Base stations are highly sensitive, and therefore they will receive messages from vessels which maybe have a very weak signal because the antenna might be at an angle, or there might be some fault, etc. But it also can receive partial messages. A normal AIS receiver will not receive a partial message. It can't do anything with it, because the partial message will not include a universal time. And if there's no time part of the message, then it's impossible to be able to geolocate that vessel on a label plan display. However, the base station will know that that vessel which is not sending a UTC, the timing message, is not receiving anything from satellite, it's just broadcasting a partial message, which might just be, this is my name and this is my course, or something like that. The base station will receive that information and it can be catalogued. And so the operator is able to determine vessels and the approximate range of those vessels, knowing the size of the AIS cell. So it is useful information, but only an AIS base station is able to do that. So coastal AIS and base stations are normally positioned to give optimum coverage. For example, the Malacca Straits or an area like that will have numerous base stations on either side of the Malacca Straits. They might be positioned close to the entry of busy ports or areas where the traffic is converging. AIS in busy waters does require channel management for Class A, ATONs, Class B, and application-specific messages. If we don't manage the channels and we don't manage the vessels in the cell, then we will end up with the AIS becoming very quickly saturated. For MDA, we need to detect all AIS transmissions to give us the situational awareness, especially Class B. We should remember that only Class A is required to be carried by certain vessels. Class B is not required to be carried by any vessels at all. It is purely voluntary. In some areas, a fishing authority might require, under subject of the license, for vessels to use Class B. But there is no international carriage requirements for Class B. Only base stations have the sensitivity to hear all AIS, even very weak signals. A ship's AIS will not receive weak signals, and a satellite cannot receive weak signals. Normal AIS receivers and satellite AIS cannot receive weak signals, and that is important. Base stations give us the ability to manage AIS and the VHF data link, VDL. We're able to organize all the ships of a certain type, cargo, when to transmit and when to be silent. We're able to assign specific ships to other channels, for example, fishing, ports, canals, etc. And we're also able to interrogate Class B that do not transmit in a slot because they have no GNSS input. If we know the vessel is there, we can request that vessel to transmit. Base stations, as I said, will detect partial messages. This lets us know that a vessel is out there, even though we might not have position information or time information from it. This is vital for MDA. No commercial AIS receivers for ships are able to do this. If we look at the AIS cell in relation to what a satellite will see, we can see like a honeycomb of thousands of cells. So remembering that the timing for the transmission of AIS from Class A or Class B, Class BCS, Class BSO is organized for ships in range of each other. And it's dynamic. As a ship moves away from one cell and joins another cell, then it will be assigned a different slot. And we can imagine that when we have something like a 5,000 kilometer diameter range of AIS from a satellite, that we're going to have thousands of cells. And therefore, we have a very high probability of collision of data from one cell and another, and maybe several cells. And so this is one reason why sometimes with satellite reception of terrestrial AIS, we will not see every vessel. But as I said, when those vessels move out of a cell and join another cell, then we might see that vessel again. And sometimes people think that, oh, look, that vessel has disappeared. They switched the AIS off. They're jumping to a conclusion because there are many technical reasons why the satellite might not be able to receive the AIS from those vessels. And the most probable reason is because there's data collision with another cell. On the first slide, I mentioned that we have message 27, which is a specific message designed for two frequencies. Message 27 is only required to be carried by Class A and can, if the vessel wants to, a Class B SO. This will mitigate satellite terrestrial AIS data collision. However, message 27 is often silenced when a vessel is in range of a base station, and it depends on how the base station is set up as to whether or not we will be able to continue to track vessels using message 27 whilst they are in coverage of a base station. It's important to realize that message 27 is impossible to be transmitted by Class B carrier sensitive. Sorry, it should be CS, not SC. I'll have to change that. Message 27 is much easier to detect by satellite because it is much shorter and has its own frequencies. It's broadcast once every 3 minutes, alternatively on channel 75 or 76. So a vessel will transmit once every 6 minutes on channel 75 and once every 6 minutes on 76, alternatively. This gives us a high probability of detecting vessels which would otherwise be in a saturated area. It is not designed for collision avoidance. It is not designed for VTS. It is designed to be able to track vessels when out of range of coastal coverage. So it supplements the coverage of AIS base stations. It is ideal for tracking in non-congested areas such as transocean passages, outside the coastal area, and is ideal for port logistics and many other commercial applications which want to know when a vessel might arrive, for them to be able to track it across the planet, but it has limited value for MDA. Message 27 lacks critical message components to enable us to carry out a vectorial analysis. For example, it does not give ship's heading. And without ship's heading, it is impossible to carry out vectorial analysis because we need speed, we need the course made good, and we need the ship's heading. With those three components, we're able to tell a lot about what our vessel is doing, whether it's drifting, whether it's got another vessel alongside, because of course drag will be on one side of the vessel, causing a shift of the heading and course made good. It will also tell us if a vessel is fishing. Message 27, as I said, is not allowed to be transmitted by Class B CS. See, I got it right there now. And so, again, that has limited value for MDA because of maritime domain awareness. A lot of the vessels which you want to track are, in fact, if they are using AIS at all, they were probably using Class B. Right, that's AIS in a nutshell. Now I want to move on to spectrum surveillance. And again, we'll look at spectrum surveillance from satellite and also terrestrially.
Robert, can I interrupt you for a second?
Yes, or two, if you like.
So before moving on to the next section, shall we give our members or give our attendees a chance to ask any questions if they have, or if they seek any clarifications on the points mentioned? Shanaka,
Sure,
what do you think?
Yes, Taranga, that's an excellent idea. So if anybody has any questions for Robert, or for myself, happy to answer them.
Go ahead, Ron. I see your raised hand.
Yeah, Robert, can you explain how the classifications are made? A, B, and C, are those based on the gross tonnage of the ship or length overall, or how is that done?
No. Class A is required to be carried by all ships over 300 gross tons and all passenger ships. Class B is not required to be carried by anybody.
Oh, Roger, got you. Thanks, Rob.
Anyone else? Nadila, do you have a question? Okay.
Yeah,
Right. Go ahead.
thank you, Darren. Yeah, this might be a bit broad, and I feel like it's a bit political as well. But question to both of you actually. There are, for example, US sanctions on certain countries, and certain goods cannot be shipped to those countries. But there are, like, I have seen like New York Times investigations on how, for example, North Korea with sanctions by pretty much having dark, like a fleet of dark ships. How does US authorities, without the cooperation of like where most of these ships originate from, that is China and Russia, like how do they find that data, and how do they use it for law enforcement?
Okay, I think that we've already said that the AIS message can provide information, but if a vessel is sanctioned, it's unlikely to be showing what it's really doing or what it's really carrying. But if we can backtrack a vessel to an area where we think there's a high probability that it might have been involved in breaking sanctions, so the cargo is loaded or whatever, then maybe we will have an opportunity to find out that information another way. Because when a vessel is in a port, everything that it's doing is recorded, and so the port authority might have information unless they're colluding with the sanctioned vessel. We can track vessels by other means, as Shanika mentioned earlier. He mentioned Hawkeye 360 and synthetic aperture radar, but SAR cannot identify a vessel. Passive sensing from satellites by Hawkeye can correlate the information and can sense a multiple spectrum. And so therefore it might be able to identify, for example, a VHF transmission on channel 70, which will give the MMSI and therefore identify the vessel. But I don't think we can really address that fully now, because it's quite
Understood.
Your question is quite complex, and we have courses which I'm sure you can join sometime, which goes into details of what is the probability of a vessel being in a certain area, etc. But we can't really cover that all now.
Understood. Okay, thank you.
Okay, back to you, Ron.
Okay, spectrum surveillance.
No, just 1 second,
I think there's Robert, I think there's some question.
Ron, the floor is yours.
Yeah.
Go
Okay,
ahead.
Rob. Okay, Rob. From a ham's perspective, I know that terrestrial AIS, the relevant authority, encourages members of the general public to host AIS receivers. We have a couple in Sri Lanka that are hosted by ham clubs and individual radio amateurs. Now, if any of the attendees tonight wishes to go and put their hand up to volunteer hosting an AIS receiver, can you tell our members how they might go about it?
AIS receivers are are available from a numerous number of sources. I think one has to be careful the quality of the AIS receiver that you're buying, and of course the siting of the antenna for that receiver is rather important. There's no point siting it 5 miles inshore in a busy city area, because you need to have a good view of the sea, of the coast. But they are available. Yacht chandlers sell AIS. You can buy AIS directly from manufacturers. It really depends on the grade of AIS that you're looking for. Base stations are quite expensive, and therefore I don't think something that an amateur would want to invest in. But AIS receivers start as low as a few tens of dollars. They will not be very good. I think you need to spend $100 to $500 to get a good quality AIS receiver. But I really can't guide you any more on that.
I think, if I may jump in, Robert, I think what Ron is asking is there are companies like Marine Traffic and Fleetmon that offer opportunities where if you host a AIS station at your house and connect it up to your modem and feed back that information to that agency, they give you some level of access to their system. So there are those options that are available. These are commercial entities. We can't promote or be part of that, Ron, but I think that's the question you're asking. There are certain companies, they monetize that information. So they entice you with the fact that they'll provide you with a free AIS station and antenna, but then you have to connect that up to your modem so that the information is fed back into their system as a terrestrial receiver AIS, and then they give you some level of access. So yeah, back to you.
Yeah, that's the one that I'm referring to. Thank you very much, Rob and Shanaka. Please continue.
Thank you,
I
gentlemen.
think we are close to 1 hour, but do you want Robert to continue, Taranga, or do you want us to stop now, or what we have? What other
No,
members
we are good.
want?
No, Shanaka and Robert, we are good, so we can continue, I think.
Okay. I won't spend too much time on this part, but historically, in fact, we've had spectrum surveillance by satellite for more than 20 years. In fact, the very first AIS detection by satellite was done by CNES in 2003. So, in fact, that is 20 years ago. Today, there are many spectrum surveillance payloads on satellites, some of them being able to range from VHF to Ka band communications, and typically that would be Hawkeye, but they're not the only ones with variable spectrum capability. There are several initiatives at the moment from the United States, that would be Hawkeye, Luxembourg, and Norway. Luxembourg, Cleos are emerging. There's also one in France called Unseen Labs. Now, some of these are looking at a specific spectrum, a specific frequency, like X-band radar. Some can detect X-band and S-band, and some can do the whole range of spectrum, as I said, from VHF to Ka band. However, none of these can cover a persistent coverage and detection. They're ideal for outside critical coastal areas where persistence is not required. We must consider that these are polar orbiting satellites. And Shanaka showed you an image, and I'll show you an animation shortly, showing how a polar orbiting satellite works in relation to the Earth. We have to imagine that the polar orbiting satellite is always on its same path, always on the same trajectory in space. It's just going round and round and round. The Earth moves around underneath it. And so each time there's an orbit, and the orbit takes 90 minutes in total, the Earth has rotated something like 15 degrees in that time. And so therefore, we then have another slice of the planet being looked at by that satellite. And so we cannot get persistence from this type of satellite unless there are a lot of satellites. And then they overlap each other, and then we can build up persistence. But that's a very expensive exercise. So in the satellite segment, we can use geolocating and sampling methods whilst the satellite's orbiting. Hawkeye, which was mentioned by Shanika, flies in formations of 3 satellites together, giving multi-spectrum sensor capability. There are a number of polar orbiting monosats, that's a satellite just traveling by itself, that can detect maritime spectrum. And there are also sun-synchronous orbit monosatellites to detect maritime bands or frequencies. Multispectral satellites information can be tasked individually or as a group. Shanika mentioned that with Hawkeye, you have 3 satellites, so you can triangulate, but you can also use one of those satellites to sample. You can still get a position from just 2 satellites, or you could actually use all 3 satellites on different frequencies to sample, so that when the next train comes around the planet, it's able to triangulate on frequencies of interest. These were not actually designed for maritime applications. They were, in fact, designed for land applications. But they're very useful in the maritime. Maritime band sensing is devoted to normally X-band or VHF spectrum. Unseen Labs will also detect S-band, but we've got to remember that S-band radar is also carried by aircraft. And so therefore, we're not necessarily seeing ships unless you classify an aircraft as a ship. These satellites can be retasked to analyze other frequencies, as I said, as they are orbiting. We can also use passive radar, not just on satellite, but also terrestrially. And indeed, recently, Shanika's team went to Bongao Island in the Philippines, and it's probably the first passive sensors to be used on land were actually commissioned and paid for by UNODC. At the moment, the investment into passive technology is mainly for X-band radar. And as we can see here, we would be able to detect the frequency and the X-band would be able to detect the characteristics of the frequency and even the characteristics of the magnetron. So we are able, once we've recorded the received signal, we're able to catalog that. And when that ship comes back in the near future, then we might be able to actually identify that vessel just by the radar signature. The great thing about passive technology is it is passive. It does not transmit, it just sits there and listens. And therefore, if it is repositioned, nobody knows where the panels are. It's not like a big rotating antenna on the top of a large tower, which is reflecting the sun as it is turning and therefore giving the presence of the station. Sorry about that. When a ship transmits RF, whether it's VHF radio or whether it's radar, the ship itself, the structures of the ship will re-radiate that signal, and that can actually create a scatter pattern. Now, we can't identify a ship just by the scatter pattern, but we might be able to identify the class of the vessel by a scatter pattern. And also what the vessel is doing, because of course, if the jib of a crane is slewed over the port side or starboard side, that will change the scatter pattern. So all the structures such as antenna, cranes, deck cargo, masts will actually contribute to the scatter pattern. So we would be able to identify sister ships, but we would not be able to identify individual ships by a scatter pattern. If there's more containers on a ship on one voyage than another, then the scatter pattern will be different. We saw an example that Shanika gave of using synthetic aperture radar to be able to detect a dark ship, a ship which was not transmitting. Here we can see another way, another opportunity of detecting dark ships. If we have a signal of opportunity, such as a large 25 kilowatt transmission from a passing tanker or bulker, then that signal would be reflected off smaller vessels that may themselves not be using radar, but we might be able to detect the reflection of those smaller vessels. This is something for the future. Nobody yet in the civil world is doing this at the moment, but a number of companies are looking at this as an opportunity, because we know that the reflection which goes back to the ship's radar that transmitted it will re-radiate in other directions as well, and at the same power as the reflection to the ship. But the way radar works, the way normal radar works, it's a clock. And so it knows what time it sent the signal, and it knows the multi-seconds, is measuring the multi-seconds until that signal comes back. With passive, we need to be able to know when the ship transmitted, and we need then to open up a window for time of reception of other reflections. So we're not looking at the radiation from the large vessel, we're looking at the re-radiation. And that is just timing. And as I say, a number of companies are looking at doing that. It is a very good opportunity of being able to detect dark vessels. Now, this animation shows how a polar orbiting satellite, as we see, it's always going over the poles, and that's why there is a station at Svalbard. If you ever go to Svalbard, it's an interesting place to visit. There are hundreds of ground stations of many different communication, AIS, and other sensors. Also at the Antarctic, there is also a station called Troll. Do we have any questions on the RF or AIS? I think we can see how
we have a question from Jalia 487 Juliet Lima. Go ahead, Jalia.
Hi, Robert. My name is Jalia. Actually, I'm a navigator. I'm working on board ships. I have one question. Now, you are using passive radars for detecting the dark vessels. I have a question that there is any way that you can use AIS signals also, like a passive AIS to detect the dark vessels.
Well, AIS is quite a strong transmission, but I'm not sure. Any RF signal will re-radiate. It's just a matter of what the strength of the signal is, and I'm not sure that it's a good question. I haven't thought about that one, but I really it would be possible, but I don't know of anybody at the moment that is looking at passive sensing on those frequencies. Some companies do have multispectral receivers, but they have to tune them in to each frequency they want to monitor. And then you have the same problem. You know, the transmission is every 6 seconds or every 3 minutes or whatever. And so trying to sort out the timing to make sure that you are seeing the reflection or the multipath from that AIS transmission, I think would be a very interesting task. But nobody, as far as I know at the moment, is actually looking at that. The reason why I showed the radar is because it is a very powerful signal.
If I may jump in the passive RF sensor that we installed on Bangabo Island in the Sulu Sea, it is correlated with AIS. So we see the AIS targets and then the RF direction finding to locate RF emissions. So the AIS signals are on screen. We know where the legal vessels are, or at least the vessels that are transmitting the AIS is on screen. Then it looks for the RF direction finding to detect vessels that are transmitting some form of RF signals or RF emissions over that screen. Back to you, Joe.
I hope that answered Jalia's question. And we have actually two questions. Let me hand over to the first one. Dilusha, over to you, Dilusha.
Hi, Robert. Is there any size limitations regard of that those passive radars can detect any vessels like that? If there need to be any, they are need to be up than certain size, so smaller ones will not detect or something like that. Is there any size limitations?
Terrestrially, the technology is extremely sensitive, and so but from satellite, there will be a problem for weak signals. So the satellite segment will not pick up a lot of things that the terrestrial segment would be able to pick up.
Oh, okay, thank you.
Is there a ballpark figure for that, Robert?
Well,
okay, I guess not.
Well, yeah. I mean, when one looks at radar, radar ranges from 25 kilowatt X band or 30 kilowatt S band. S band also is used by yachts and fishing vessels, but it's a completely different beast. It's only transmitting at 600 watts, and so therefore it is unlikely for that 600 watts to be received by satellite, but it might be received by a terrestrial passive sensor. But we're delving into it's something to be aware of, but passive sensing is still a new science.
there is somebody else with the hand up, Dimuthu.
Sorry, my name is Dimuthu. I think you can hear me. I just have one question. How is this propagation conditions impact on AIS
Sorry, I
systems
just
such as
lost my
like
connection.
geomagnetic storms?
Dimuthu.
Yeah, my question is how is the propagation condition impact on AIS systems, like from geomagnetic storms, things like that?
Well, geomagnetic storms are normally more prevalent in the polar areas. So geographically, it will have a difference. But these storms affect HF frequencies much more than anything else. Once you get to the equatorial areas, the effect is much less. But of course, a very powerful storm will incapacitate the satellites, and that obviously will have a major effect. But terrestrially, VHF is quite safe, except it means that we won't have GNSS because those will be knocked out by the storm. But that's one reason why VHF data exchange systems have been designed, because it is possible for a coastal station to range or to use the coastal station for ranging. So we're able to still navigate using VDES, irrespective of having a satellite component. But propagation, as you know, the worst propagation is with HF. The propagation of HF is widely. It has massive effects on the accuracy for long range navigation and also quality of long range communications.
Okay, thank you so much.
Thanks, Dimuthu and Robert. Robert, do we have any more slides to present? Or
No, and indeed, I have to run.
okay, so I have just one question for both of you. So is it possible to share any real life or anything from your experiences? Any interesting scenario that you had to come across, or any unforgettable incident? This could be a cliche question as well, but anything interesting that comes into your mind while working on these technologies and with these agencies? Robert and Shanaka, this is an open question for you, for both of you. Anything that you can
I might
disclose?
just go in first. I think I don't know whether it's an unforgettable incident, but I think where what is important is when agencies seek our assistance to take satellite imagery, they find it very difficult to provide us with a polygon of probability. So they, for example, the vessel has gone dark. They have lost the AIS signal, say 7 hours ago or 6 hours ago. By the time they get in contact with us asking for a satellite image of that area, and by the time we task a satellite company to take a satellite, and the time that satellite company has a satellite orbiting over that polygon, it's quite a long duration. It could be up to 24 hours or even longer between the time they lose the AIS target or the vessel of interest that they were following, by the time they contact us, by the time we task a company, and the time the company has to task a satellite that can be positioned over that region. What we find is a lot of the law enforcement agencies just cannot provide us with the most accurate polygon of probability, because the image that we can provide them, if it's a SAR image, a satellite radar image, a synthetic aperture radar image, is a polygon of, say, 100 kilometers by 150 kilometers. And that's a small space in the ocean. And very often they give us a wrong polygon. And when we go and get a satellite image for a drug operation, there's nothing there. And this happens to us very often. And each image costs us about $2,500 US to acquire. So what we are now doing is to try and train and use a lot of the AI technology to do predictive work in terms of making sure that the polygon that they provide, to the best of all the knowledge and capability available, is very much the area that the vessel may be in. Of course, there is no guarantee, but at least, so we've had quite a lot of misses where we lost the vessel because there is very little understanding about the drift, the wind, previous historical track data that is used to determine the polygon of probability. So those are some of the issues that we have come across in terms of supporting drug operations at sea. Robert, do you want to add anything to that?
Not really, except in fact, we at one time we were tasking synthetic aperture radar imaging over certain areas when we were training in the past, when I used to work with Shanika. And we found two vessels, which just two little dots in between Samoa and American Samoa and Samoa. And the PTCCC got quite excited about this because they were not aware those vessels were there. But they were not able to take any action, unfortunately, to be able to investigate them further. But it is quite surprising sometimes when you get an image of showing a vessel in a proximity where you did not expect to see a vessel at that time. So it's you always get surprises, but yeah, there are other things which we can't really talk about. But with that, I really have to go. It's been a pleasure listening to your questions, and thank you for the opportunity of allowing me to speak. And I hope that one day we might be able to do this again.
Well, Robert, thank you so much for joining and spending time with us. And we loved every moment of it, Robert. So with this, I will let you go, and I'll hold on Shanaka for a little while. Thank you so much on behalf of the Radio Society, Robert. And well, who knows? Let's meet some other time once again for a nice session like this. So we loved it. Thank you so much, Robert.
It was a pleasure, and thank you for the opportunity, Shanika.
Thanks, Robert. Thanks very much for joining.
Cheers.
So do we have any more questions to Shanaka, gentlemen? Any questions before we wrap up for today?
I'll jump in. Shanaka, that station or the setup in the Philippines, was that the first of many to come, or can you elaborate a little bit as far as you can?
Yes, Ron. So RF direction finding, I think you did a Fox hunt recently. So I think many of you are experts at RF direction finding. So this is very similar to that. We are looking for RF emissions and triangulating to detect vessels out at sea. To better understand the concept is that vessels that have AIS transponders tend to switch them off, believing that law enforcement agencies will not be able to detect their location. But people who've been out at sea would advise you that at night it's pitch black, it's pitch dark. And unless you have something to alert other vessels that you're in that area, you can have a collision. So what vessels do is they switch their AIS off, but they switch on their radar to ensure that no other vessel is coming to collide with them. So basically, using that concept, we are looking for RF emissions from the Philippine site. Yes, we are going to install more RF sensors, and it is also very environmentally friendly, because in many of these locations, to run a 25 kilowatt radar would require a generator and a whole lot of fuel to be transported, because these areas do not have electricity, and they are remote islands. A RF sensor, because it's simply a receiver, it does not require that much of electricity. So several solar panels could simply run an RF sensor and a modem to get that signal back to the control center. So it's environmentally friendly as well, and a cheap option as opposed to a very expensive cost of a recurring cost of maintaining a radar. But the only drawback, Ron, is that terrestrial-based RF triangulation can only be done in choke points because of the curvature of the Earth. Unless you can triangulate from a different direction in open waters, it's very difficult to triangulate. But what we are now trying to do is we want to have one RF sensor on the coastline, and a second one as the payload on a drone. So when the drone goes out, it can triangulate with the coastal AIS, and it also gets a better coverage. So rather than having two static RF passive RF sensors, we have one static RF sensor on the coastline and one mobile RF sensor affixed to a UAV. So that's the next phase of what we're trying to do, Ron. Back to you.
Thanks for the information on that, Shanaka. Very insightful, and makes me realize the giant strides you guys have made and how far behind we are, but we're trying to catch up. Thanks for the presentation. Also, I'll take this opportunity. I need to duck out also 1:30 in the morning, but thank you very much, Shanaka, for coming with Rob and sharing all this information with us. It's a lot to absorb, I know, but if we have absorbed 50% of the information provided to us, I think it's been a great and something to work with for the future. Thanks again, Shanaka, and pass on my regards to Rob as well. And over to you, Taranga.
Thank you, Ron. Thanks so much for coordinating this on. So we'll catch you maybe later on. So have a good night. Good night sleep, Ron. Thanks again.
Thanks, Ron, and see you soon. Bye.
Bye-bye.
Well, do we have any more questions to Shanaka or any points to clarify? Any more questions, gentlemen? Okay, I guess that's it. Okay, Shanaka. So with that, anything? No. So yeah, let's wind up the session for today. And thank you so much once again for you, Robert, and also for Ron for coordinating all this. So I believe all our members, all our attendees got a very, they could spend their time on a very productive session today. And they got their leads to, if anyone is interested, they can go on and find more information based on what we discussed today. So that's the least we could do. So thank you so much, Shanaka, Robert, for doing all the hard work. So with your background in working with these international organizations, agencies, and also with governments worldwide, you brought a wealth of knowledge to our members of the Radio Society. I'm thankful on behalf of all the members once again, Shanaka. So
Thank you very
any
much,
last?
Taranga. And thank you for hosting us. And it was quite an enjoyable evening. And I hope all of you were able to get some understanding on the multiple uses of AIS, especially for maritime law enforcement purposes. Thank you.
Thank you so much. So let's meet once again some other time with an equally interesting session. So we'll keep in close touch, Shanaka. So thank you very much, all the attendees as well. You've been wonderful tonight. Thanks for the questions. Hope we had a productive session, and let's wind up the session with this today. Thank you so much.
Thank you. Good night.
Good night, everybody.
I think the local VHF net is in progress.
Thank you.
Okay,
you.
good
Bye-bye.
night.